oh, sorry, 6 squares, not 7. The last session, the second theorem we'll talk about on this board, it too also uses the broad strategy of proof by contradiction. Okay, so we will assume the opposite of this. In other words, this particular language is decidable. So you're getting used to that, I dare say. We've done it quite a few times already. So here, no exception. So it's nice to have some familiar things, so you don't have to devote so much mental effort on them because they are familiar, right? Okay, so we will assume the opposite of this because we're using proof by contradiction. Therefore, this language is decidable. And what does that mean? Again, revision. A language is decidable, by definition, if there's some Turing machine, ordinary Turing machine, infinite tape Turing machine, that decides it. Again, revision. In other words, that Turing machine accepts all the strings that belong to that language, and that Turing machine rejects all other strings. Right? In other words, it never loops. Right? It's a decider. That Turing machine is a decider. It makes a definite decision. Yes, it accepts or rejects every string. Right? And if it accepts, that string belongs to the language. Okay? And it's via that type of reasoning that you get the equivalence between a language and a computational problem. There's so much the same in Sipser's mind that he'll take a language and label it a problem. And you saw that happen last board. Right. Okay. Now, reduction. That's been that's the whole theme of the chapter, right? The very title of the chapter. Yeah. Reducibility. Right. So, a very fundamental concept for this chapter. Reducibility, again, at the risk of boring you. What is it? What is that? Well, you hear the term reducibility or reduction or to reduce, and instinctively you think in terms of two problems, okay? A and B. And if problem A is reduced to problem B, what that means is that the solution to problem B, the second one, which is assumed known, right? So you know everything about problem B, let's say. And so if you can take your first problem, problem A, and reduce it to problem B, you can then get a solution to your problem A via or using the solution to problem B. Okay, that's reducing problem A to problem B. Or saying it a different way, same thing, using different words slightly. You can say you have a reduction from problem A to problem B. Okay, that terminology also used. Okay, now in this context, for this particular problem, we are going to reduce this problem. So we're going to go from, so this will be our problem A, and we're going to reduce it to this problem, or language, right? Language problem, yeah. Okay. So this will be our problem A, or this is language A if you like, and this will be our problem B, language B. Okay. And that will be we will use that for the proof. That's the basic strategy. We're going to use reduction from problem A to problem B. Now, we also knew, again revision from previous board, if you can reduce a problem A to a problem B, and you happen to know that problem A, first one, is undecidable, then you know that problem B must be undecidable. Now that wasn't actually proved, as I keep saying, it wasn't actually proved by Sipser. I'm wondering if it's another one of his jumps where he just assumes it's so obvious that he doesn't bother discussing it, which he tends to do quite a bit, which is annoying. In my view, one of the faults of Sipser as a textbook writer. Let's think about that a little bit. So you reduce problem A to B, you know that A is undecidable, therefore the problem B, or language B, must be undecidable. Is that blindingly obvious or not? Why did he not discuss it? Because it's basically, we're using this bit of knowledge again and again, as it's really important, but it's just tossed off without proof. Now, is it obvious? So if your A is undecidable and you're reducing A to B, so how could you have B be decidable if A is undecidable? That doesn't seem very plausible, does it? It seems fairly obvious, but well, I'll leave. Yeah, it's an ongoing. I'll leave it there for the moment. It seems very plausible that because if you're reducing A to B, and how can B be decidable if A is undecidable, and yet you're reducing A to B? So you're solving A using the solution to B. It seems plausible. Okay. All right. Okay. So we're using proof by contradiction. Okay. So we assume the opposite of this. So we un this. So we assume it's decidable. Now, if this is decidable, then the strategy of the proof is we will try to show that ATM is decidable. Okay? That's critical what I've just said. The broad strategy of the proof is that if this is decidable, then we will show that ATM, this problem, is decidable. Okay? Now, we know from prior knowledge, earlier proof, we know that this language, this problem, is undecidable. Okay? Hence we have a contradiction. And therefore we go back and negate our earlier assumption. And the earlier assumption was that this language is decidable. So we negate that, and therefore this language is undecidable. So that's how we prove this is undecidable. Okay? Hope you've followed that logic. All right. Okay, so now the proof boils down to how to, given this, how do we prove this? Okay? Given that this language is decidable, how do you prove that this language is decidable? And that's in terms of language. If you think in terms of computational problems, if this problem can be solved, in other words, there is a Turing machine that decides this language. How do you, from that, how do you deduce, prove that there's a Turing machine that decides this language? Okay. Now we know that's undecidable because effectively that's just the famous halting problem. Okay. We've talked about that before. Okay, so here's what the proof. I was saying before. Here's what the proof boils down to. How do you this is your problem B, and so we're going to reduce effectively this problem, which is the halting problem. How do we reduce this to this? So how do we solve this problem? In other words, showing that ATM is decidable. How do we reduce that to this? And this is now just a given. Right? It's given because it's assumed. This resulted from negating what we're really trying to prove. Okay. So that's problem B, and this is problem A. So we're reducing problem A to this, and that's a given. How to do that? Alright, so the rest of this square here is what I'm calling the logical skeleton, right? The essential core reasoning, the chain of reasoning in this proof that you really need to get your mind around, so that you understand it, and then from that the rest are just more details. But the essence of the argument is in the next few lines. All right, so how do you start with this and you deduce this? So if this problem's solvable, this will become solvable. Or looking another way, you're reducing this problem to that problem. Okay, that's problem A. That's problem B. B has a solution. Well, we just assume this language is decidable, and that in turn came from just our starting assumption with the proof by contradiction. Okay, so right. Okay, now we get into now the step-by-step reasoning starts. Okay, well, it goes further. We're assuming this, right? The basis of the proof by contradiction. So this language is decidable. Remember that by definition means there's a Turing machine that decides it. Okay, and we're going to use that Turing machine to build another Turing machine that will decide this. Okay, now what I've just said is critical. Playback if necessary. Okay, I'll say it again. We know